Hello students, welcome to the subject of Mathematics 3, myself Dr. Ankit Acharya, and today we will discuss about a very important topic of this chapter, Cauchy linear equation. Okay, the general form of Cauchy linear equation, this type of equation, an equation of the form A0, A0, A1, these all are constant that you can see A0, A1, A2 up to an minus 1, an, okay, these all are constant, and x raised to n, if your nth derivative, that means dny by dx raised to n, then x raised to n is in form of multiplication, okay, then x raised to n minus 1, x raised to n minus 2, if dy by dx, then multiply with x, okay. So the difference between homogeneous linear differential equation and Cauchy linear equation is, in homogeneous linear differential equation, either you have any term, either you have constant or the derivative, okay, and the derivative, constant and derivative, constant and derivative. But here you can see that suppose your function, suppose your term, in your term nth derivative, like dny by dx raised to n, dny by dx raised to n. So this is the nth differentiation. So multiplication with x raised to n. Suppose dn minus 1 by dx raised to n minus 1, then x raised to n minus 1 in form of multiplication, okay. So the difference between homogeneous linear differential equation and Cauchy linear differential equation is this, okay. So now how we can solve this type of Cauchy linear equation? So there is a method that you have to remember, okay. So first of all, first we take, let x is equal to e raised to z, right. So of course when we take x is equal to e raised to z, so log x is equal to z, right, and the here you can see that x square d square, right. So x square into first of all try to understand about x into dy by dx. So x into dy by dx, so x dy, d is a capital, and instead of this I can write d dash, where d dash is what, d dash is now d by dz, okay, d dash is now d by dz. So this some of the formula that you have to remember, I just write here x dy by dx, so that is equal to d dash, okay, d dash y, where d dash is nothing but d by dz. Now similarly x square d square y by dx square, instead of x square d square y by dx square, I write d dash into d dash minus 1 into y, where d dash, okay, that is equal to d by dz, don't forget, okay. Or sometime instead of d dash also you can take any other operator d1 or just say d, okay, x dy by dx. So if you take dy, but make sure that you have to mention that capital D is not d by dx, it's a d by dz, okay. Similarly x cube, just I write here, suppose we have x cube d cube y by dx cube. So x cube d cube y by dx cube, we write d dash minus 1 and d dash minus 2, okay, into y, right. Now you can understand, if x into dy by dx, we take d dash y, where d dash is a d by dz. If x square d square y by dx square, then d dash minus 1 into y, where d dash is d by dz, and x cube d cube y by dx cube, then d dash minus 1 d dash minus 2 into y, okay. So x square y double dash minus 20y, that is equal to 0, x square d square minus 20 into y, that is equal to 0. Now x square d square, so d into d minus 1 minus 20, d square minus d minus 20, okay, d square minus d minus 20. So m square minus n minus 20, that is equal to 0. So m minus 5 into m. Now when we factorize this first factorial, so m square minus n minus 20 equal to 0. So m minus 5, okay, and m plus 4 equal to 0. So 5 and minus 4, right. So clearly first you have to write complementary function in term of z, okay. So c1, because of 5 and minus 4 are roots, so c1 e raised to 5z plus c2 e raised to minus 4z, and we know that e raised to z is what? E raised to z is x, okay. I just mentioned here e raised to z is nothing but our x, Okay, so that's why this is nothing but c1 x raised to 5 plus c2 x raised to minus 4. Clear? Okay. So, right. Now, also we can find particular integral, but here we don't need to find particular integral because right side your function is a 0. So, particular integral, that is also 0. Particular integral is 0. Okay. So, general solution y is equal to complementary function plus particular integral. So, c1 x raised to 5 plus c2 x raised to minus 4. This is your general solution. Now particular here we have to find particular integral. See right side not 0. Okay, x square y double dash minus x y dash plus y, that is equal to x. So again y double dash. Now what is y double dash? We know that y double dash is nothing but d square y by dx square. Okay, and x square. Okay, multiply with x square also. So x square y double dash. So x square d square y by dx square, and instead of x square d square y by dx square I can write d dash or d minus 1. Okay, here also you can write just d minus 1, but make sure don't forget here your capital D is nothing but d by dz, not d by dx. Okay, similarly x y dash, so that is nothing but x dy by dx, and we know that x dy by dx I can write dy. Okay, so d simple, y will be common, so instead of x square d square they write d minus 1, instead of x d they write minus d plus 1 into y, that is equal to e raised to z. Okay, here you can see that this is capital D. Okay, and here italic D. Okay, so they change the letter, right? Now d square minus 2d plus 1 into y, that is equal to e raised to z. So m square minus 2m plus 1 is equal to 0. So m minus 1 square equal to 0. So 1 1 real and distinct root. Okay, real and 1 1 real and repeated root. So complementary function, first we have to write in term of z. So c1 plus c2 z into e raised to z. And now we know that c x is e raised to z and z is log x now. So when e raised to z, instead of e raised to z I can take x, and instead of z I can take log x. Okay. So this I can write c1 plus c2 log x into e raised to z is x. So x, right? So c1x plus c2 x into log x. So y1 is x and y2 is x log x. Now particular integral. Okay. Particular integral, that is 1 upon d square minus 2d plus 1. So 1 upon d minus 1 whole square, 1 upon d minus 1 whole square, and this is exactly x. Now, but we write x in terms of z because this d is now not d by dx, it's d by dz. So right hand side function x, but I write e raised to z. Now this is exactly the case 1. I apply the case 1 shortcut method. Okay, don't forget in last lecture we discussed about shortcut method, 4 cases, case 1, 2, 3, 4. First case is for e raised to ax plus b. Second case is sin ax plus b, cos ax plus b. Third case is for polynomial, and fourth case is for e raised to ax into b. Now this is case number 1. Okay, just instead of x here we have z. Okay, so a is equal to 1. A is equal to 1 when we compare with e raised to az. Instead of x here we have z. So a is equal to 1. So what is our rule? Instead of d, okay, instead of d, we have to write 1, the value of a. But 1 minus 1 denominator becomes 0. So what happened? Now we multiply with z. Okay, just multiply with z. Okay, and the differentiation of this term d minus 1 whole square. So that is 2 into d minus 1 and e raised to z. Now once again denominator becomes 0 when we put 1 instead of d, when we put the value 1 instead of d. So again we have to multiply with z. So outside now we have z square. Okay, 1 upon, right, differentiation of 2 into d minus 1. So that is 2 and e raised to z. Right, now z is what? Z is log x. So log x whole square divided by 2 and e raised to z is x. So x. Here, so log x whole square divided by 2 into x. Here, okay. Let's take one more example. X square d square minus 7xd plus 12 into y, that is equal to x square. Okay, so x square d square minus 7xd plus 12. Okay, so instead of d square, I can write d into d minus 1. This is some italic d, this is capital D. Okay, so d into d minus 1. Now this d is nothing but d by dz, right? And d, 7d plus 12 into y. So and x square, so e raised to z whole square. So d square, when we calculate this term, okay, this is, you can see that d into d. So d square minus d minus 7d. So minus 8d and plus 12. So plus 12. So we write f of m. Our f of m is m square. Instead of d, just we write m as usual. So m square minus 8n, m square minus 8n plus 12, that is equal to 0. So m minus 6, m minus 2 equal to 0. So 2 and 6. Okay, m is equal to 2, 6 are real and distinct root. So that's why C1 e raised to 2z plus C2 e raised to 6z. C1 e raised to 2z plus C2 e raised to 6z. Now instead of e raised to z, I take x, so C1 x square plus C2 x cube. Okay, and now particular integral, when we find particular integral, okay, 1 upon d square minus 8d plus 12 into e raised to 2z, right? And that is z. Okay, so 1 upon d square minus 8d plus 12 into e raised to 2z. So again, here you can see that when we take 2 instead of d, okay, denominator becomes 0. See, 1 upon 2 square minus 8 into 2 plus 12. So 4 plus 12, 16 minus 16. So denominator becomes 0. So that's why one z will be outside. This is case 1. Okay, z 1 upon 2d minus 8. 2d minus 8 into e raised to 2z, right? So z 1 upon 4 minus 8. Okay, 4 minus 8 into 2 raised to 2z. Okay, because now e raised to z is, okay, e raised to 2z. This is e raised to 2z. So minus z by 4, right? 4 minus 8. So minus 4. So minus z by 4 e raised to 2z. And what z, the value of z is log x. So minus log x by 4 x square. So c1 x square plus c2 x raised to 6 minus x square by 4 into log x. So this is particular integral. Now next is very important equation, Legendre's linear equation. So in Legendre's linear equation, difference is in Cauchy linear equation we know that if dn by dx raised to n or n minus 1 derivative dn minus 1 by dx raised to n minus 1. Okay, suppose dn by dx raised to n, then in multiplication we have x raised to n, then x raised to n minus 1. Okay, but here in Legendre's equation, okay, in Legendre's equation, not just x, we have ax plus b raised to n, and now instead of x raised to n minus 1, now we have ax plus b raised to n minus 1. And suppose similarly if dy by dx, so in Cauchy linear equation we have x, but in Legendre's equation now we have ax plus b. Okay, so this all are, okay, the terms clear. And now you can understand this general equation a0 into a plus bx or ax plus b, both are same. Okay, a plus bx raised to n or ax plus b, right? So a plus bx raised to n dn by dx raised to n plus a1 a plus bx raised to n minus 1 dn minus 1 by dx raised to n minus 1 up to a and y, that is equal to qx. So now here you can see that 2x plus 3 whole square d square y by dx square minus 2x plus 3 dy by dx minus 12y, that is equal to 6x. So 2x plus 3, here what happened? We have to take 2x plus 3 is equal to e raised to z. Okay, so when we take 2x plus 3, that is equal to e raised to z, and taking log on both the side, so log 2x plus 3, that is equal to z, right? And 4, okay, 4d into d minus 1 minus 2d minus 12. So 4d square minus 4d minus 2d minus 6d minus 12 into y, that is equal to, here you can see that x, the value of x you can find out from this equation. The value of x is what? Easily e raised to z, okay, e raised to z minus 3 divided by 2. Okay, so this is the value of x. e raised to z minus 3 divided by 2. So 6 into e raised to z minus 3 divided by 2. So 3 e raised to z minus 9. Okay. In the auxiliary equation, this auxiliary equation 4m square minus 6m minus 12. So 2m square minus 3m minus 6 is equal to 0. So m, now here we have complex root. See, a is equal to 2, b is equal to minus 3. Okay, this is your a, this is your b, and this is your c. C is equal to minus 6. Okay, we compare with ax square plus bx plus c. So now root we can find with this manner that minus b plus or minus square root of b square minus 4ac divided by 2a. So this is equal to minus b means 3 plus or minus square root of b square. B square is what? 9 minus 4, a is 2 and this is minus 6. So 2 into minus 6 and divided by 2a. So 4, right? So this is equal to 3 plus or minus 9 plus 48 and divided by 4. So this is equal to 3 plus or minus root 57. Okay, root 57 divided by 4. So that's why here you can see that 3 plus or minus root 57 divided by 4. And this is real and distinct root. Okay, factorization is not so simple, not so easy, but real and distinct root. It's not a complex root. Okay, b square minus 4ac greater than 0, then you have real root. B square minus 4ac equal to 0, then you have equal root. And if b square minus 4ac less than 0, then you have complex root. Okay. So c1 e raised to 3 plus root 57 by 4 into z plus c2 e raised to 3 minus root 57 by 4 into z. So this is c1 2x plus 3 e raised to, this is e raised to 3 plus root 57 by 4 plus c2 2x plus 3 raised to 3 minus, sorry, raised to, okay, because e raised to, here we have, okay, the value is, see, x is nothing but e raised to z minus 3 by 2, okay. So 2x plus 3 raised to 3 plus root 57 by 4, okay, into z, and here also e raised to z is 2x plus 3, so that's why 2x plus 3 raised to 3 minus root 57 by 4. And now when we find particular integral, this is the case number c, 1 upon 4 d square minus 6d minus 12. So 3 into 1 upon 4 d square minus 6d minus 12 e raised to z minus 9, 1 upon 4 d square minus 6d minus 12 into e raised to 0 into z. Okay, so that's why 3 into 4, 3 by 4 into 1 minus 6 into 1 minus 12 e raised to z, and this is minus 9 by minus 12 e raised to, this is case number 1. Okay, so minus 3 by 14, when you calculate minus 3 by 14 e raised to z plus 3 by 4, and we know that e raised to z is nothing but 2x plus 3. So minus 3 by 14, 2x plus 3 plus 3 by 4. So the general solution that we know that complementary function plus particular integral. So up to this is complementary function. Okay, this is your complementary function. This is your particular integral. So the general solution is nothing but complementary function plus particular integral that you have to write. So in today's session, we discuss about last topic of this unit number 7, a higher order differential equation. So that is Cauchy linear equation and Legendre's linear equation. So in this chapter, we discuss about first of all homogeneous linear system of equation. After that, we discuss about undetermined coefficient, then variation of parameter, shortcut methods. Okay, 4 cases, important 4 cases, and in today's session, we discuss about Cauchy linear equation and Legendre's linear equation. So unit number 7 is complete now. Up to this, thank you.